In this tutorial, I'm going to talk about some stuff we didn't get to yet in class number 2, which is complex wave number and refractive index. So let's start right off by considering two sine waves. Here's sine wave A1 in white, and here's its formula, something that should be very familiar, that A1 as a function of position and time in one dimension, one spatial dimension, has some amplitude A0 and then a dependence on time, which is cosine kx minus omega t. And this might be a drawing. Notice the horizontal axis is now x, not time as it was in class. Of course, this is just a snapshot of this. Let me remind you what the movie of this would look like. If I animate this, this is what we're talking about, where the different positions on, like this one here, there's a vertical oscillation of the field. That would be the variation as cosine of omega t. And if I freeze it, there's a variation in position, which is the dependence on cosine kx. You put the two together, you get a moving wave which travels to the right. So I can now ask the question, what would be the expression for an identical A2 wave which is delayed relative to A1, so as they travel through space, it's really lagging behind it? First, let's talk about some other things we know about these waves. It has a velocity moving to the right. I'll draw a little arrow here and indicate that there's a velocity. And the speed, the magnitude of the velocity, as you know, is the angular frequency divided by the wave number. And the refractive index is defined as the speed of light ratioed to the velocity of how fast this wave is going. And then by substitution, that's equal to C0 over omega over k. And I want to emphasize that we can write that as written as C0 over omega times k. So refractive index is proportional to k. That's going to turn out to be why, if you have a complex number for the wave number, you're going to have a complex refractive index. And the rest of this tutorial is to talk about situations where you really do have a complex wave number and a complex refractive index. So what is the expression for A2? A2 as a function of position and time, well, it's also going to have the same amplitude A0. And there's going to be a phase delay. Let's again suppose that the phase delay, the magnitude of the phase delay, is pi over 10, like it was in class today. We know it's going to be A0. We know it's going to be a cosine function, just like this one is. And as was said very nicely in class today, now we've got kx minus omega t. How do we decide whether it's a positive or negative phi? Well, we know that this function is delayed relative to A1. I'll remind you that in class today, if this was the time axis, then the red curve would be shifted a little bit to the right of the white curve. Now that we're plotting it as position, the meaning of being delayed is more like a physical picture that you're used to. This could be like two waves on strings traveling along, and obviously if they're moving to the right, the A1 is ahead, so the red one is delayed. And as was said very nicely in class today, from the floor, if you're delaying something, you oppose the sign of the time term. So this is plus pi over 10. So that's A2. And the thing I want to point out here is that if we do go complex, this relationship between A2 and A1 is very nice to write. So if we write a complex A2 function of x and time, that's going to equal A0 times e to the I kx minus omega t. And I'll separate it out here to say that the phase delaying is that we also multiply by e to the I pi over 10. But notice that these first two terms, that would just be the complex way of writing A1. So A2 becomes equal to e to the I pi over 10, that is to say the phase delay, times a1 of x and t. So this emphasizes that you have a complex number, which is the relationship between these two waves. It really is a proportionality, and that proportionality has some physical meaning, even though it may seem a little bit weird to multiply something by a complex number. And of course, this relationship between two waves is one that we can easily picture in optics. You could imagine beam A1 corresponds to just some light path, I'm trying to draw a straight line, traveling through space, and we could have a beam A2 which consists of the same beam up until a point, but then maybe it encounters some little window that slows down the propagation of the light, and then it continues along. But for the same amount of time of flight, it doesn't go quite as far as the A1 beam, and this would be the A2 beam. And if you wanted to compare the situation of the A1 beam and the A2 beam, you could say that the transmission function of the glass, the beam that you get after the glass, as opposed to the beam that you would have gotten if there were no glass, would be to say that beam A2, the second beam, is the first beam times this factor. This e to the I pi over 10 factor tells you the influence of this piece of glass upon the beam of light that was passing through it. The net effect of that piece of glass was to delay the beam by this much. So it's a real physical thing that you can really use to describe an actual piece of glass, and depending how thick it is and what it's made out of, that's going to influence, of course, what this number is. Now, it could, of course, be the case that this piece of glass also absorbs some of the light. So if it absorbed light as well, perhaps it knocks down the field strength by a factor of 2. Then we would say that the overall effect of the piece of glass, then, instead the factor would still be e to the I pi over 10, but there'd also be a factor of 0.5 out in front of it. So 0.5 times e to the I pi over 10 would be the effect. Now what's happening, if we zoom in on what would be happening inside that piece of glass, if light is both being affected in phase and in amplitude, we can sort of draw that region of glass over here. And what we would say is that the light field comes in like this, but as it travels, and I'm exaggerating it a bit here, so it's decreasing by more than a factor of 2, you would get some sort of delay like this, so that what comes out of the glass is less than what came into the glass. And that exponential decay there, like this, that is a complex envelope. If we zoom in on that, the net effect might be to decrease the electric field by 0.5 or by a factor of 0.2. But this decay over here, we can write that as having some spatial dependence on position. This decay is like e to the minus alpha x. So alpha is the decay coefficient of a decaying exponential. Instead of an imaginary exponent for the exponential, we have a real number in the exponential, and that represents decay. How do we write the entire expression for this decaying electric field as a function of position and time? So how do we write that entire electric field decaying here? Maybe we'll call that A3. So A3 of x and t, the field as it propagates inside of there, well, let's say that it starts off with some amplitude A0. For reasons we can discuss later in the class, if a beam of amplitude A0 went from air into glass, it wouldn't keep the same amplitude. But let's say once it starts off in the glass, it has some amplitude, which we'll just still call A0. And then cosine of kx minus omega t, let's say, e to the minus alpha x. So it would be a combination, if we're using real numbers, a combination of a cosine function times a decaying exponential. The beautiful thing about using complex numbers is that we can write this in a much more compact fashion if we go to a complex notation. So I will now clear the board and get started on that. So here we are again with our oscillating and decaying wave in this region in the glass, and here's our real expression for it. If we want to write that as a complex expression, then we would say A naught, and then the cosine would become e to the I kx minus omega t, but then I've got another exponential e to the minus alpha x, and I can just group those terms, so I can write that as A naught, and here we go, e to the I. Now I'm going to have two x terms. One is k times x, and the other one is negative alpha times x. So I've already got an I, so if I factor that out, I've got to multiply that by plus I alpha, and those two terms are the x terms, and there's still a minus I, this a minus I omega t, so here I would write the omega t. So again, notice what's happened here. You've got a kx and an alpha x minus alpha x. When you take care of minus signs and imaginary numbers, you end up getting this expression here, which we'll call the complex wave number. Complex wave number. I'm not giving it a separate number, a separate variable. We're going to refer to it as k or k tilde, but usually just k. And for here I'll say k tilde formally equals the real k plus I times that absorption term. Both of these have units of inverse length. Something happens per unit length. This is radians gained per unit length. This is amplitude lost per unit length. And so now we have a complex wave number. Again, it's a complex number, but it really is telling you something about a real physical object. You got to break that feeling that complex numbers are only existing to take the real of at the end and you throw away the imaginary part. Here the imaginary part has a definite meaning because it's telling you a relationship between an unattenuated sine wave and an attenuated sine wave. And if you remember this relationship up here between direct proportionality between k, the wave number k, and refractive index n, that suggests that we have something called a complex refractive index n tilde, and that would just be equal to two real quantities. C naught is a constant, speed of light. Omega is the angular frequency. That's always just a number of radians per second. That's a real number. But the complex wave number goes in where we used to just write k. Now we write k plus I alpha. So you now see that there's a real part of the refractive index and an imaginary part of the refractive index. So a material can have, if a material is one where a light wave going through it will attenuate as well as propagate, that is to say have wavelength behavior, then the refractive index we properly say is complex. So again, it's a complex number, and it doesn't just mean to take the real at the end and throw away the imaginary part. It means the way we use refractive index in this class is one where the imaginary part of n is very meaningful as well as the real part. I'm going to finish up this tutorial doing some MATLAB work, so let me bring some MATLAB windows in here. And what I'm going to do is I'm going to start by simulating a situation where a wave is traveling from the left to the right here, and at the midpoint the incident wave encounters a medium with refractive index n2, and at first it's going to be going from air into glass. So when I do that, I get behavior like this. You see I've got an incoming wave, and then the transmitted wave has a lower amplitude. That's something we'll learn about later in the course. But it's a simple unattenuated sine wave. If, however, I put a small amount of imaginary refractive index into this second medium, we will learn later in the course that the following happens. And now, as you see, the wave is propagating, and as it oscillates, it also is exponentially decaying. You can see the envelope right here. And that's something that really happens, and what you're really seeing is the amount of transmitted light versus the amount of reflected light. The last thing I want to point out is that if you make this the imaginary refractive index quite large, like equal in amount to the real part of the refractive index, the behavior starts to be even more striking. You get almost nothing propagating into the material here, only about 1 wavelength's worth, and you get a fairly strong reflected wave. And if you actually make the material dominated by its imaginary part of its refractive index like this, you get something that looks a lot like the way a mirror behaves. You can see now that the incident wave is almost entirely reflected and almost nothing goes into this second medium, and there doesn't seem to be any propagating wave here at all. And this really is the way that mirrors work. This is exactly how to understand the refractive index of a mirror. For now, I just want you to understand that something that looks very funny, a complex number for a refractive index, is something that in Optics 262 has real physical meaning, both the real part and the imaginary part. Complex numbers aren't just for taking the real, they're for using in the middle of equations for finding relationships between, say, incident and reflected beams, and they have lots of physical meaning.